But you've had an opportunity to look at these different types of accessory lines and think about how do we know that these are necessarily different things in a triangle. So I want to start with the two kinds of bisectors. The perpendicular bisector of one of the sides of a triangle that the diamond's worked on, and the angle bisector of its opposite vertex, which is what the heart's worked on. So here's the diagram that demonstrates that those two might be different things. So first of all, group, talk me through, in this diagram here at the top, why is this red line the perpendicular bisector of BC? What does perpendicular bisector mean?
So what we said was a perpendicular bisector is when you equally split the triangle into two equal halves. It can't not be equivalent to each other. So we were saying an isosceles triangle or an equilateral triangle, it's going to equally split into two perfectly even triangles.
Okay, so let me riff on that for a second. So first of all, anytime we use the word bisector, we do get to use this notion of equal splitting, right? When we were using words like half kind of loosely earlier in the semester, and I was chiding you for it, if we have the word bisector on the table, we can say half. Because what does the perpendicular bisector of the side BC equally split into two pieces? So the perpendicular part justifies why when it does split, whatever it splits, it's doing so at a point that has a 90-degree angle. So what we can say is, first of all, the perpendicular part of perpendicular bisector means that angle ADC and angle ADB are both what? They're equal angles. And because together they form the straight angle BDC, that means that each is a right angle. We could say 90 degrees if we want it to be lowbrow. So let's just say right angle. Okay, so that's the perpendicular part of the bisection. But what's the bisection part tell you? What's actually being split into two equal pieces here? As you said triangle, I'm going to dispute that. The length of BC, right, so the segment BC. So we'll put little congruence marks here that show us that the bisector implies that BD and DC have the same length. So when we say perpendicular bisector, those are the two pieces. Perpendicular justifies why it's a right angle, and then the equal segments that we split it into is the sense in which we have bisected something. Okay, great. And so your conjecture is that if our triangle is isosceles, then the perpendicular bisector and the angle bisector are the same thing. Okay. So let's rewind to the angle bisector. In what sense is this line the angle bisector of the angle A? What's being bisected there? Well, I'm sorry. The angle at A. Yeah, I got to be careful with this laser pointer. The angle at A is being bisected. So what we would do is, on this diagram, put in two congruence marks for these angles. When I do that, I like to put in a little angle and then a slash through that angle to indicate that the angle BAD and the angle CAD are congruent. Angle BAD. So bad equals CAD. Bad equals CAD. So angle bisector means that we have split this angle into two pieces. Perpendicular bisector means we split that segment into two pieces. And in the triangle on the top, which is isosceles, by the way, if ABC is meant to be an isosceles triangle, which two sides are you holding up as equal there? AB and AC. So I'm going to put congruence marks on those sides as well. So a double slash here and a double slash there to indicate that ABC is an isosceles triangle with AB equal to AC. We've constructed the perpendicular bisector of the side BC, and therefore we have these congruence marks here. Now let's go to Sabrina's point. When she was talking about the bisector, she said it splits the triangle in half. In what sense do we know that this triangle has been split in half? What would we say? What's our formal geometric statement that would tell us that this triangle is split in half? Okay, yeah, so what did you just say? Sorry. Side angle side applied to what?
Like that angle.
Applied to,
Top angle, because you know
Yeah,
that,
and-
you know the two sides are equal, you know that the line is equal, obviously, in the middle, and then the two angles on the top are.
okay, all right. So we have a couple different ways of looking at this. The fact that the fact that this was the angle bisector lets us use these green angles, which are congruent to one another, and according to side angle side, applied to those three things. So this side, the angle in between them, and that side, right? That side angle side will tell us that these two triangles are congruent, based on it being the angle bisector. Side angle side shows that those two triangles are congruent to one another. But what about if that were the perpendicular bisector? The fact this is the perpendicular bisector sets up what kind of congruence? If we can't use these angles, how do we know that they're still congruent? So I guess what I'm saying is, if we don't have these congruence marks there, can we still conclude that these two triangles are congruent?
Yeah, by side, side, side.
By side, side, side. There we go. So that suggests a proof for the assertion that this team made, that if we start with an isosceles triangle, then the angle bisector and the perpendicular bisector are both the same thing, because both of them split our triangle into two congruent pieces. And how we know they're congruent is different depending on whether we consider that line to be the angle bisector and use SAS, or whether we consider it to be the perpendicular bisector and then we can use SSS. But either way, it's the same thing. But in general, the perpendicular bisector and the angle bisector need not be the same thing as this last diagram down here at the bottom shows for us. Because in fact, the perpendicular bisector of the side BC does not always even pass through the other vertex of the triangle. And if it doesn't pass through the other vertex of the triangle, it's not going to bisect the angle at the other side of the triangle. Right? So in general, these two things are different. But for an isosceles triangle, the evidence points to them being the same. So our last pair are altitudes and medians. And by altitude, we mean a line which originates from one vertex and is perpendicular to the side opposite that vertex. So for example, in this diagram down here at the bottom, the altitude originating from A is this line, and it's the altitude simply because it makes a right angle with the opposite side. Meanwhile, what's a median? How do we define a median? It bisects, well, it doesn't bisect the angle. What does a median bisect? It doesn't. So here it doesn't look like, right, it's not bisecting this triangle. We can't make that congruence argument that we made before on this diagram. At least it doesn't seem that we can. But we can say that it bisects the opposite side. So it's a bisector without being a perpendicular bisector necessarily of that opposite side. So there's altitude, there's median. Under what circumstances did your team say that those two things are the same? So your diagram here in the bottom looks as though those two things are the same. Why? Yeah, again, you're pulling out an isosceles criterion. And I think that we're justified in doing so because if this line were a median, then it would bisect the side BC, but if it bisects the side BC, then we can make, again, this side-side-side argument about congruence. And if it's congruent, then the angles at D correspond to one another and must therefore be congruent. And two congruent angles that add up to a straight angle are both right angles. And since they're right angles, this side is also an altitude of the triangle. So I'm going to agree that under the circumstances, an isosceles triangle's altitude and median, originating from the same vertex, are going to be the same thing. But the diagram on the top here should argue for why that need not always be the case. In this figure, by the way, is this figure that you drew here on the top, is this a right triangle to start with?
Yeah.
Okay, so you're assuming this is a right triangle, which is why, in fact, the altitude coincides with what?
The side.
It coincides exactly with the side, AB. And if that's the case, then certainly a side cannot bisect another side of the triangle. So there the median and altitude are very different, but for an isosceles triangle, we can show that they're the same.